Hi everybody, if you've been following these videos in sequence, we've now completed the full calculation of an example one-way ANOVA. We've also run through the post hoc tests and we've interpreted everything up to this point. Now in this video, I'm going to review some measures of effect size for an ANOVA. Well, I'll walk you through how to calculate those and how we obtain all of that and what they mean and how to interpret them. Now, of course, we're using data from previous videos. Otherwise, this will be just a nice review if you haven't been following these in sequence. So let's go ahead and get going. So an effect size measure is the exact same thing for an ANOVA as it is in something like a t-test or anything else. It is some measure of the effect, the size of the effect of the independent variable on the dependent variable. In this particular case, of course, a one-way ANOVA, the independent variable is the grouping variable. It's a categorical variable or sometimes ordinal variable. And then the dependent variable is the continuous measure that we've used. Now in this particular example, we used a grouping variable of different amounts of fertilizer used in different soil samples, and there was a control group. And then the dependent variable was the length of time it took in days to reach 6 inches for these plants. Okay. Now, there are several different types of effect size. There are different ways to measure effect size, and they all have advantages and disadvantages. I've covered just one for the independent samples t-test and dependent samples t-test and so on. We're going to cover two measures, however, for the one-way ANOVA, and these work for any kind of ANOVA as well. Of course, they're calculated ever so slightly differently for different ANOVAs. Okay, so we're going to try two different types of effect size. The first one is omega squared, and then we're going to try a Greek letter eta. We'll try both of these. Let's start out with omega squared. Now, omega squared means that this is the Greek letter omega. You'll notice it's a lowercase omega. The larger omega, the capital omega, looks more like a horseshoe or something like that. Okay, this is a lowercase omega squared, so not a W squared. Anyone who calls it that is incorrect. This is the Greek alphabet, not the Roman alphabet. Okay, and this is the equation for it. Relatively straightforward stuff. So what we're looking at here is the sum of squares from the between groups variance minus the degrees of freedom for the between groups variance multiplied by the mean squares within. Now, of course, you'll do this first, then subtract that product from this. And then down here is, of course, the sums of squares total variance and the mean squares within put together. Okay, now of course we can find all of this because it's all in our equation for the F value. So if you have to calculate the F value by hand, you can obtain all of these elements. They're back in your work. However, of course, it's much easier if we just do this from our source table, which I walked you through in the previous video. So again, if we've made the source table, it looks like this from our data. This is just an example from our data that we've been working with over the last couple of videos. But all of the elements that we need for the equation to solve omega squared are right here in this video, in this table, excuse me. The sum of squares for the between groups variance is, of course, right here, SS between 175.14, and so that goes right there. Then the degrees of freedom for the between groups variance is right here, DF between groups, 3 goes right there. Then the mean squares within is, of course, right here. Mean squares within groups variance, 1.19 goes right there and again right there. So you can see mean squares within appears twice in the equation. Last thing we need is the sums of squares for the total variance, which I guess, again, SS for total, 203.7 right there, goes right there. Now all we need to do is simplify this equation. Okay, and the math here is pretty straightforward, of course. The first thing we can do is in the numerator, multiply 3 by 1.19, and then there's only one thing to do in the denominator, so we'll do that in this next step. 3 times 1.19, of course, gives us 3.57, and of course I've rounded a little bit just for fun, and 203.7 plus 1.19 is 204.89. So that's as simplified as we can get in that one step. Now we simply find the difference between those two things in the numerator, which is of course 171.57. 171.57 divided by the denominator of 204.89, of course, gives us 0.84. So our omega squared value is 0.84. We'll interpret that in just a moment. First, as a little math check, you may notice that the omega squared cannot be larger than 1. Mathematically, that cannot work out. It's possible for it to be 1. That would be very weird, though. I would find that extremely strange. It also cannot be negative, of course, because it's called omega squared. After you've squared a negative number, it cannot be a negative still. And so even if there were to be some kind of, I guess it's impossible actually for this result to be larger than this result over here. So this would have to be a positive result. If you found a negative result, you did something wrong and you need to go back and check what's up. Now let's interpret omega squared. Now, omega squared is pretty nice to interpret because it's simply the amount of variation that we saw in the dependent variable that we can attribute now to the independent variable. And so as it gets to be more, that means there's more variation attributable to that independent variable, meaning it had a larger effect. So because our omega squared value equals 84 or 0.84, that's 84% of the variation that we saw in the dependent variable, or growth time, is attributable to the kind of fertilizer, not the kind of fertilizer, but the amount of fertilizer that we used in the soils for this little example, of course. And so 84% of the variation is enormous. That's almost all of the variation. I have never seen an effect size this large in real research. Of course, I just made up the data for this particular scenario. So can we come up with some kind of terms for this kind of size? Yeah, and of course we can. Now, as you can see here, it doesn't take a whole lot to find a large effect size. So in other words, if you had an effect size of, or an omega squared specifically of 0.15, that means 15% of the variance is attributable to the independent variable. Now, that's large. That's considered large because that's quite a bit of variation. In this case, because we exceed that quite a bit, 0.84 is much larger than 0.15, we can of course say that's an enormous effect. Almost all of the variation we saw in the independent variable or in the dependent variable is attributable to the independent variable. All right, so now we can add to our overall interpretation. So this is revisiting the interpretation that we had so far if you've been following these videos in sequence. So we had an ANOVA where we had different amounts of fertilizer, the same fertilizer, but different amounts in different groups. And we had 4 different amounts of fertilizer. We used the same plants, and then we timed those plants to their growth, hitting a growth of 6 inches to see which ones got to that faster based on the kind of fertilizer. The idea here is we can attribute any differences there, if we see them, to the amount of fertilizer. Turns out that we were able to do that because we found a significant F value of 49.04. That was statistically significant because it was larger than the critical value that we would need for a test with 3 degrees of freedom for the between groups variation and 24 degrees of freedom for the within groups variation. Now, we can reject the null hypothesis and say we did not find equal means. We actually did find different means. We then did our post hoc tests and found that specifically it was the half-ounce group that was doing better than any other group. In other words, they grew faster than any of the other groups. So we already figured that out in the past. However, now we summarize everything and we can say at this point that we also saw a very large effect of the fertilizer amount on the growth rate of the plants. So this does not appear to have been an accident. You could say simply by the statistical significance, and we saw a very large effect. So not only did it make a difference, it made a very big difference in how much fertilizer we gave to these plants. Okay, so now we can also interpret this to say that there's 84% of the variation in the plant growth rate is attributable to the amount of fertilizer that we used. And of course, our post hoc tests tell us that specifically we can say that it was the half-ounce group that did the best. Now let's try one other measure of effect size. Okay, and the next measure of effect size is called eta. As you can see here, it's a Greek letter also, just like the omega squared. In this case, we're not squaring anything, however, as you'll see in the calculations. This is a Greek letter eta. It is the lowercase eta, of course, in the Greek alphabet. So it looks like a lowercase n in the Roman alphabet, except with a little longer leg there, as you can see. Here's the equation, very straightforward. All we're doing is taking the square root of the proportion of the sums of squares between variance to the sums of squares total variance. In other words, that essentially just gives us the proportion of the between groups variance to the total variance. And so again, you would expect a very high number means a large effect of the between groups effects to the total variation. So pretty similar in many ways to the omega squared, however, not quite the same thing. As you can see, it's not eta squared. Eta squared is a thing, but not in this particular example. But we're just going to cover the eta. All right. So yes, it's simply the ratio of the between groups variance to the total variance, which is very interesting and helpful. Okay, so we can do this easily if we have our source table, which is why I made an entire video about that and its importance. All we need here is, of course, the sums of squares for the between groups variance, which again is right there. We needed that for the omega squared anyway. 175.14. Then the sums of squares for the total variance, which is right here, 203.7. Okay, and simply do that. We plug in those values, 175.14 divided by 203. We'll do that on the next slide here. And here we go. 175.14 divided by 203.7 equals, of course, 0.8598. We take the square root of that and get 0.93. Now you may notice here also this cannot be larger than 1. That's simply impossible because the sums of squares between variation must be smaller than the sums of squares total variation. That is absolutely necessary. And so we would definitely get a value lower than 1. In any case, we have a 0.93. Now we can interpret this differently. Please do not mix up the interpretation ideas or the interpretation terminology for omega squared and eta, because they are different, as you can see right here. However, once again, we do find an excessively large effect size. So 0.93 is, of course, much bigger than our minimum value required for a large effect size here. And so again, we have a very large effect of eta. Now again, same thing in the comprehensive summary. This isn't really changing anything. I've just termed it a different way. So we tried to find the effect of different fertilizer amounts on the growth rate of several plants. They were the same type of plant, 2 6 inches in a one-way completely randomized ANOVA, and we found a significant effect. We summarize everything here. The F value was 49.04. The test had these characteristics: 3 degrees of freedom for the between groups variance, 24 for the within groups variance, degrees of freedom, that is. The p-value was less than 0.01, meaning there's less than a 1% chance of committing a type 1 error by rejecting the null hypothesis, which we've done. And our effect size here was, of course, 0.84 using the omega squared reference. Now, we also recall that Pertucci's post hoc test told us that it was the half-ounce fertilizer group that did better than any other group. And there are, of course, some more things that we can summarize about it, but that's in a previous video about the post hoc test. So that's essentially our take-home message. All right, that's it for one-way ANOVAs. Now we'll talk a little bit more about some other things in the next video. Thanks, and I'll see you then.